So we know R2 is a vector space because R2 satisfies all 10 axioms from the definition of a vector space. So here we have a subset of R2. So these are ordered pairs, points in the plane, if you want to think about them that way, whose second coordinate is 0. This is really the x-axis. We want to know if it's a vector space. So we could look at the definition of a vector space and make sure that all 10 of those axioms are satisfied by this set W. So is it closed under addition? Yes, it is, because if you take two vectors that look like this, you get another vector that looks like this. Is the addition commutative? Is it associative? Is the zero vector in there? Is the additive identity in there? We could check all of these, but since this W is a subset of R2, and we already know R2 is a vector space, we don't need to check all of these axioms because a lot of the axioms will get inherited from sort of the parent vector space. So since the vectors in W are all vectors from R2, just not all of them, but the vectors in W are from R2, we know that this has to be true. This addition has to be commutative because it is an R2. Same with this one. Same with these properties of scalar multiplication are all going to get inherited. So the only axioms that don't necessarily get inherited from the parent vector space are axioms 1, 4, 5, and 6. And so, it's almost half of them that you still need to check. But if you think about this being closed under addition, so let's check to see if it's closed under addition. If you take two vectors that look like this, so you have x and 0 plus y and 0, you get x plus y and 0 plus 0 is 0. So it is closed under addition because when you add two things that look like this, whose first coordinate could be anything, and second coordinate is 0, you get something whose first coordinate is a real number, any real number, and the second coordinate is 0. So it is closed under addition, and so that's a yes. And it is closed under scalar multiplication. So I'm going to take something in there, x0, and I'm going to take a scalar k from the reals, and when you multiply those together, you get k times x, and k times 0 is 0. So it is also closed under scalar multiplication because when you take a scalar and multiply by a vector in there, you get another vector in there. So the answer there is yes. So I would have to check that the 0 vector is in there, which it is because 0 is a real number, so 0, 0 satisfies this condition that just the second coordinate is 0. And I could check that the additive inverse of any vector in there is in there, and it is, because if you take some general vector, x0 in there, its additive inverse would be negative x0, and so that's satisfied. So you might think that to check for a subspace, you just have to check those four axioms: the closed under addition, that the additive identity is in there, that the additive inverse is in there for any vector in there, and that it's closed under scalar multiplication. But if we were to take, note, since we know it's closed under scalar multiplication, if we take 0 times some vector, you get the 0 vector. So because it's closed under scalar multiplication, the 0 vector has to be in there. And same with the additive inverse. If I took negative 1 times x0, you get negative x0, which is the additive inverse. So really, in order to check that a subset of a vector space is itself a vector space, you just need to check those two axioms. So we have a subspace test, closed under addition. That's the first thing you have to check, and the second thing you have to check is closed under scalar multiplication. So there we have the subspace test. Those are the only two axioms that you need to check if what you're checking to see is if something is a subspace of something that is known to be a vector space. So let's do another example here. Get this on here properly. So we have another set here. This is a subset, again, of R2. And we want to know whether it's closed under vector addition and closed under scalar multiplication. So in order to be in W in this case, your first coordinate can be anything, the second coordinate has to be that thing squared. So like 1, 1 is in W, 2, 4 is in W, negative 2, 4 is in W, 3, 9, etc. 0, 0 is also in there. So the 0 vector is in there. Is it closed under vector addition? Let's just add these two guys together. 1, 1 plus 2, 4 is 3, 5. Is that in W? This is not in W. So W is not closed under addition, which means that this is not a vector space. So the subspace test makes it easier if you know you're pulling things, if your set that you're looking at is being pulled from a known vector space. So it's good to know some vector spaces that we'll use, and there are essentially three. There's like Rn. So we've been dealing with R2. That's a plane. This is three-dimensional space. This is four-dimensional space. So all those are vector spaces, and these are just ordered. In this case of Rn, it's just ordered n tuples. So this is ordered pairs, would be ordered triples, ordered quadruples, and so on, with the standard operations are all vector spaces. And then we have, like we've looked at, M sub, let me do P, Q. This is P by Q matrices, so we've looked at M2, 2. I think we looked at that in one of your homeworks. This is the set of 2 by 2 matrices with real entries under the usual operations. So those were all vector spaces. And then we had P sub, I think we looked at P sub 2 and maybe P sub 3 also. So I'm going to say P sub n, which is polynomials of degree n or less. And that less or less is important because otherwise the set ends up not being closed. So let's look at a subset of the 2 by 2 matrices. So let's look at W equals, let me do A, B, C, negative A, such that A, B, C are real numbers. So here's a subset of the set of 2 by 2 matrices with real entries under the normal operations. Is this a subspace? So we want to know if W is a subspace of M22. We need to check for closure. So we take two general objects in here. So in order to be an object in this set W, the 1, 1 entry can be anything, the 1, 2 entry can be anything, the 2, 1 entry can be anything, but the 2, 2 entry has to be the negative of the 1, 1 entry. So there's your relationship. So some matrices, it would be in there like 1, 2, 3, negative 1, or 3, 2, 5, negative 3, or negative 4, 0, 1, 4. So, like I say, in order to be in W, all that has to be true. You can have basically any numbers you want here, here, and here, but these two guys have to be the negatives of one another. So is it closed under addition? I'm going to take two things in there, A, B, C, negative A, and I'm going to take another general thing in there. So if I want to show that this is closed under addition, I can't just take like two of these particular examples and add them together and show that you end up with something in there. I have to take general ones, and I can't take A, B, C, negative A again because it would be definitely restricting what I'm looking at. So I got to take a general vector plus another general vector. So I'm going to use M, N, P, and negative M. And you add those two things together, and you get A plus M as your 1, 1 entry, B plus N, 1, 2, C plus P, and negative A minus M, which doesn't quite look exactly like this pattern because I would need to have this be the negative of that. So I'm going to rewrite it one more time just to really convince myself and make it look exactly like it needs to look. This negative 1 can factor out, and you'd have A plus M in there. So when I take two things that look like they have to look in order to be in this set W and add them together, I get something that looks like it's in this set W. I have a real number here, another real number here, another real number here, and the real number here is the negative of the real number there. So it is closed under addition. And then we want to check scalar multiplication. And so I'm going to take, again, a general vector in there, multiply it by a scalar. And so this is under the usual operations. So remember, scalar multiplication of a matrix multiplies every element in the matrix by the scalar. And so again, the way it follows out of the operation doesn't quite look exactly like it needs to look to be in that set. So I'm just going to rewrite this once. Like that. And so it is, yes, closed under scalar multiplication, because when I take a general vector in this set, multiply it by a scalar, I get I stay inside of the set. So I don't get bumped out of the set either by the addition or the scalar multiplication. So the answer here is yes also. Now up here, we saw that it wasn't closed under addition. We didn't bother checking the scalar multiplication, because it doesn't matter if it's closed under scalar multiplication. If it's not closed under addition, then it's not a vector space. So both of these, this is an and, both of these have to be true. If either one of them fails, then you don't have yourself a vector space. So that is the subspace test, and you will have homework up to practice and check subspaces on. Okay, very good.